welcome to the deep dive. Today we're looking into something pretty exciting in medical imaging, a new way to automatically map out structures in 3D scans. It's called SegMamba.
Yeah, and it really could be a significant step. Think about it. Getting an accurate 3D map inside the body, that's absolutely fundamental for computer-aided diagnosis. It helps doctors see what's going on, plan treatments. It's crucial.
Exactly. Like if you're dealing with a tumor, you need to know precisely where it is in 3D. But getting that level of detail automatically, well, that's been tough with the older methods, hasn't it?
It really has. The standard approach, using convolutional neural networks, CNNs, they're good at finding local detail, small patterns.
Right.
But they often miss the bigger picture, how distant parts of a scan relate to each other, even attempts to broaden their view, like using those big 7x7x7 filters in 3D UXNet. It helps a bit, but it's still not quite capturing the full global context.
Okay, and then on the other hand, we have transformers. They are good at the big picture, using that self-attention mechanism. We've seen them in models like UNIT or SwinUnit or...
Transformers definitely get the global information, but the problem, especially with these really detailed 3D medical images, is the cost, the computational cost.
It's too demanding.
Massively. Self-attention has this quadratic complexity, meaning the resources needed, memory, processing power, they just skyrocket as the image size increases. Trying to relate every single point in a big 3D volume to every other point, it becomes impractical, really resource intensive.
Okay, so limitations on both sides.
Yeah.
Either not seeing globally enough or doing it too inefficiently. And this is where SegMamba comes in, taking inspiration from Mamba, which has been making waves elsewhere, right?
Exactly. Mamba is a different beast altogether. It's a state space model, an SSM. And it's shown amazing results in natural language processing precisely because it can model those long-range connections in sequences, like understanding a whole paragraph, not just adjacent words.
But efficiently.
Yes, that's the key. It's much more efficient than transformers. It uses a clever selection mechanism to decide what information is important, and it's designed to run fast on current hardware.
So the researchers thought, hang on, if this works for language sequences, maybe it can work for the sequence of data points in a flattened 3D image.
That's the core idea behind SegMamba. Could we bring that efficient long-range modeling power to 3D medical scans?
And SegMamba is their answer. A new framework.
A totally new framework, yes. It combines a sort of standard UNet shape, which is common in segmentation, but integrates Mamba to grasp the global features across the whole 3D volume and at different scales, too. And, it's important to stress this seems to be the first time Mamba has been specifically adapted and used for this kind of general 3D medical segmentation task.
Okay, fascinating. Let's get into the nuts and bolts then. What are the key components that make SegMamba work?
Well, a really central piece is what they call the Tri-Orientated Mamba module, or TOM.
Tri-orientated.
Yeah, because the original Mamba basically looks along a sequence in one direction. But a 3D image isn't just one direction, right? You've got height, width, depth.
Makes sense.
So TOM takes the 3D image data, flattens it into sequences, but then processes these sequences along 3 different axes, sort of forward through the slices, backward through the slices, and also within the slices. It's trying to capture those spatial relationships from multiple perspectives.
Okay, so it's adapting the 1D Mamba idea to the 3D reality by looking in multiple directions.
Oh.
Got it. There's also this gated spatial convolution module, GSC. What's its role?
This is crucial. Because Mamba works on those flattened 1D sequences, you risk losing the inherent 3D spatial information, like where things are relative to each other in the original volume.
Right, you squash it flat, you lose the shape.
Exactly. So the GSC model comes before the Mamba layer. It uses specific types of 3D convolutions to capture and sort of reinforce those local spatial relationships. Think of it as preserving the 3D structure before Mamba looks for the long-range connections.
So GSC handles the local 3D details, then TOM looks for the global connections across these detailed features.
That's a good way to think about it. And these two, GSC and TOM, are combined into the main building block of the encoder part of SegMamba, called the TS Mamba block Tri-Orientated Spatial Mamba block.
Okay, so the encoder takes the image, runs it through an initial stem layer to get some basic features.
Right, using a deepwise convolution, a fairly standard start.
And then passes those features through a series of these TS Mamba blocks, each doing that GSC then TOM process.
Precisely. Refining the features and understanding context at multiple scales as you go deeper into the network.
And one more piece mentioned is the feature level uncertainty estimation, FUE. Sounds interesting.
It is. The idea is as the network extracts features at different stages, some features might be more reliable or certain than others. Maybe the network is very sure about a large background region, but less sure about a tiny, ambiguous boundary.
Okay.
The FUE module operates during the skip connections. That's where information from earlier, shallower layers is passed to later, deeper layers in the UNet structure. FUE tries to estimate the uncertainty or reliability of these skipped features.
And then what? Does it filter them?
It sort of weights them. It downweights features that the model estimates are uncertain and gives more emphasis to the reliable ones. It's a way to make better use of those skip connections, preventing noisy or uncertain early features from messing up the final prediction too much, like the model double-checking its own work.
A kind of internal quality control on the features. Clever. And then, after all this encoding and uncertainty weighting, there's a decoder.
Yes, the decoder part takes all these rich processed features from the encoder and uses more standard convolution layers to actually build the final 3D segmentation map, the outlines of the structures we want.
Okay, that gives us a pretty clear picture of the architecture. Now, a big part of this work wasn't just the model, but also a new data set, right? CRC 500.
Yes, and this is a really valuable contribution in itself. They pointed out a lack of large public data sets for 3D colorectal cancer segmentation from CT scans. Existing ones were often small or private.
So they built their own.
They did. CRC 500 has, as the name implies, 500 3D CT scans. These were collected over about 12 years, all anonymized, of course.
And annotated by experts.
Yes, carefully annotated by one specialist doctor, and then all the annotations were double-checked and calibrated by a second expert. That ensures high-quality ground truth, which is vital for training and testing these models. The paper even shows some nice visualizations.
And what are the specs of this data set? Any key characteristics?
Let's see. The in-plane resolution is consistent, 512 by 512 pixels. The number of slices varies quite a bit, from under 100 to over 200, with the average being around 160 to 170. The pixel spacing also varies a bit, both within the slice and between slices. They provide all these stats, comparing it favorably in size to other public colorectal cancer datasets.
Sounds like a solid benchmark data set for the community. Right. So the big question, how did SegMamba perform on CRC 500 and other tests?
They tested it thoroughly, not just on CRC 500, but also on two other major benchmarks. BRATS 2023 for brain tumor segmentation and MRI.
Right, that's a standard one. Different imaging modality, too.
Exactly. And AIIB 2023, which is for segmenting airways and CT scans of very different structure, like a branching tree. Testing on all three really shows how generalizable the method is.
So, across the board, how did it do against the competition? Like the CNAs and transformers we talked about earlier?
It performed extremely well. On BRAT-S 2023, it got the highest DICE scores. That's a measure of overlap accuracy for all the tumor subregions. Whole tumor, enhancing tumor, and tumor core.
Better overlap, okay.
And importantly, it also got the lowest HD95 scores. Lower is better there. It means the boundaries predicted by SegMamba were closer to the actual tumor boundaries. More robust, less likely to have big outlier errors. And this was compared to strong baselines, including UXNet, UNetR, and SwinUNetR variants.
That's impressive for brain tumors.
Yeah.
What about the airways, the AIIB dataset?
Similar story there. Highest IOU, another overlap metric, and also the best scores for things like detected length ratio and detected branch ratio. Those specific metrics suggest it was better at capturing the thin, continuous branching structure of the airways without breaks.
Which is tricky, I imagine.
Very tricky, yeah. Easy to lose the smaller branches.
And finally, back on their home turf, the CRC 500 dataset for colorectal cancer.
Again, top performance, best DICE score, and best lowest HD95 score. This is particularly relevant because colorectal cancer regions can sometimes be quite small or subtle in CT scans. SegMamba proved better at identifying and accurately outlining them compared to the other state-of-the-art methods they tested against.
And you mentioned visualizations. Did they look convincing?
They did. The paper includes side-by-side comparisons on examples from all three datasets, and you can visually see SegMamba often produces segmentations with clearer boundaries and better capturing of complex shapes compared to the others.
Okay, strong results. But did they dig into why it works so well? Those ablation studies you mentioned.
Yes, they did ablation studies specifically on the CRC 500 dataset. This is where they systematically remove or disable parts of their model to see how much each part contributes.
What did they find?
They started with just a basic Mamba backbone and then added their components one by one. Adding the GSE module, the one for spatial information, gave a really significant boost in performance.
Confirming that capturing spatial details before Mamba is key.
Definitely. Then adding the tri-orientated Mamba, Tom, improved things further, showing the benefit of looking in multiple directions. And finally, adding the FUE module for uncertainty estimation gave another incremental improvement. It shows each component is pulling its weight.
Makes sense. Each piece adds value. What about the efficiency claims? Did they measure memory and speed?
They did. They compared SegMamba's training memory, inference memory, and inference time against methods like UXNet with large kernels and SegMamba transformer-based.
Was Mamba actually more efficient?
It was very competitive. Despite handling potentially very long sequences from the flattened 3D data up to 260,000 elements in their tests, SegMamba had comparable or sometimes even lower memory usage, especially during inference, and comparable inference speed.
Wow, even with those huge sequence lengths.
Yeah. And crucially, they noted that trying to use pure standard self-attention, like in vanilla transformers, on sequences that long just wasn't possible. It ran out of memory.
Oh. So Mamba's linear complexity really makes a difference there compared to the quadratic complexity of standard attention.
A huge practical difference for these large 3D volumes.
Okay, this has been a fantastic breakdown. To kind of wrap things up, what are the main takeaways here about SegMamba?
I think the biggest point is that this is really the first general-purpose 3D segmentation method built successfully on the Mamba architecture. It proves that Mamba's talent for efficiently modeling long-range dependencies can be effectively translated from 1D sequences like language to complex 3D medical data.
And it delivers results, right?
Wow.
Not just efficient, but accurate.
Absolutely. The performance across 3 diverse and challenging datasets, brain tumors, airways, colorectal cancer, was state-of-the-art, beating or matching strong CNN and transformer methods.
Plus, it's efficient, particularly memory-wise, which is critical for real-world deployment.
Exactly. Good inference speed and manageable memory make it much more practical. And we shouldn't forget the contribution of the CRC500 dataset itself, a valuable new resource for the research community.
Definitely seems like a significant piece of work. It really gets you thinking. So here's something to chew on. Given this blend of accuracy and efficiency SegMamba offers for understanding complex 3D scans, how might architectures like this change things down the line? Could we see faster, maybe even real-time, diagnostic assistance for doctors? More precise surgical planning fueled by this deeper understanding?
It certainly opens possibilities.
And maybe beyond these specific tasks, where else could this approach, this efficient long-range modeling, make a difference? Other medical imaging challenges, or even completely different scientific domains dealing with large spatial data sets. Lots to consider.
Absolutely. The potential is definitely there, and it will be exciting to see where this line of research leads.